Hello, welcome back to another video. Congrats on your Rust skills so far. At this point, we've covered the basics of the language and we're starting to get into the tricky stuff a little bit. Today, we're going to be going over smart pointers and more specifically the box type that we saw in the last video. To start this off, we're going to see how to implement a linked list in Rust. More specifically, we're going to be implementing a type of linked list called a cons list. Basically, we're going to have a enum called list that has two variants in it. It's going to have a cons structure, which is going to have also another reference to list or nil, which means we've ended the end of our list. So programmatically, if we wanted to create a linked list of 5 and 10, it would look something like cons 5, and then in that for the second part, we're going to have a cons of 10, and then for the third part, we're going to have nil. So it's kind of a recursive list, if you will. Now, if we try to do this with what we currently know about Rust, I'm going to pull up a diagram here. If we try doing this what we currently know about Rust, we're going to run into a problem. So this is going to be our stack, right? And let's say get rid of this struct cons. So we're on the stack, right? And we made an enumerable type with list that's going to have a cons of a 32-bit integer and then also pointing to another list or nil. But we're not able to figure out how big list is supposed to be if we're putting this on the stack, right? So if we're saying this, we're basically saying, okay, this list can be, or this cons variant on list can be, we don't know the size of it. It's going to point to another list. Okay, well, how big is that list? Well, that other list can have a cons value in it or nil. Well, what happens if it is a cons value? Then it's going to point to another list, and that goes on and on and on forever. And we're going to run into a recursive dependency error. So if I go ahead and actually try writing this out, so if I tried writing enum list, our cons list here, and we say it's going to either have a type of the value, which is going to have 32 integer, otherwise point to another list, or we could have nothing. Then if we try saving this, we have a infinite size error here. I'll also verify that with cargo check real quick. And we get a recursive type list has an infinite size. This is where box comes in handy. Like we introduced in the last video, box allows us to store data on the heap. We could technically do something like this. I'll just comment this out for now. We could do something like let b equal box, not two x's, new 5, and we just stored 5 on the heap instead of the stack. And the value of b would be, pardon the pun, a memory address that holds the value 5 somewhere on the heap. Now, the Rust compiler is, again, going to be friendly to us. When we did our first cargo check here, and recommend that we provide some sort of indirection by doing a cons box list. So if I go ahead and uncomment this, and say that, hey, cons should point to not just another list, but something on the heap, a pointer, if you will, to something on the heap that, in this case, stores a list. And I go ahead and save and do a cargo check again. All's fine and dandy. We're basically doing something like, instead of trying to figure out how big this cons variant in the enum list should be, we're doing something like this. Like, okay, now we have this box and we're pointing to, let me get out a little arrow here, this list on the heap, which in turn can point to either nil or point to another box, and which is also on the heap. But at this point, this is all that's going to be on the stack is our if we make a cons variant, we know the definite size. It's the size of 32-bit integer plus the size of a pointer to list on the heap. Now we can happily create, now that we're pointing to something that doesn't cause an infinite size of something on the stack, we can go ahead and happily create our cons list now. So I'll go ahead and just make life simpler. I'm going to bring cons and nil into scope. So I'll say use list cons and nil. And I'll go ahead and delete our B here. And I'll go ahead and say let A equal cons, and we're going to just do 1 and 2. So I'll do as the first argument we have our value, and then the second argument is a box, right? So we got to do a box new, and what goes in this new box? A list goes in this new box, and we could either have cons or nil here, and we're going to do a new cons, and I'll do 2, and then for the second value it's got to be a box again, and we're going to point to a list, and this time we're going to use the nil variant. And then we can iterate through our cons list doing something like this. So I'll say let mute current. This is going to be a pointer to the current index in our list here. And then we can use pattern matching with while here. So I'll say while let cons value next. So we're destructuring these off of cons. If that's equal to the current, and then we're going to print out the current value, if I can type, and then we're going to assign current to be next. But wait, you might be saying, what exactly is going on here? What's going on with this current.next? Isn't that a box? Isn't next a box because of the cons value? If it is indeed a cons, we're going to get either our integer or our box. Well, indeed it is. This is where Rust starts getting a little bit trippy. We can treat box just like a reference. We don't actually call any method on box to get the value out of it. If we truly wanted to get the value out of the box, we could do something like this. We could do something like, I'll do let B again equal box new, do 1, 2, 3. We can get the value of B by dereferencing it. We've officially moved the boxed value from the heap to the stack right here. Box is a type of a smart pointer, which basically just means that it's a reference with some fancy add-on features. Because it's a pointer, we can actually treat it like a reference, like we're used to with something. If we did let foo equal foo bar, then we know that this is a string slice reference. Same kind of deal with B. It's a reference. Box under the hood implements this deref trait, which allows us to grab the value out of the box by dereferencing it with the star operator. It's also what makes it a smart pointer. The same principle applies to getting the value out of our box, which is again a smart pointer, and we can treat it just like a reference, and allows us to do pattern matching on current right here, which to us is just a reference to a list. A little tricky, right? This is called deref coercion, and it's the same principle that allows us to use a string instance in some function that takes in a string slice. The same kind of thing is happening here, where current is technically a box, but we call this deref method on it that's implemented via the Deref trait and allows us to get the value out of the box much the same way we're able to get the string slice foo bar out of our string from str duh. Same way we're able to get the string slice out of this string instance if we passed it to some function that takes in a string slice or our string primitive type here. If we wanted to write out our own box now, it looks something like this. We would have struct. This isn't going to live on the stack like an actual box, but is still good for reference and for practice. So we would say our box takes in some type and it just holds that type. That's all that this struct is saying. Now we can say we're going to implement and we're declaring a type T for my box that takes a type T, and we can have our new function here which takes in an X of type T, returns a my box of type, you guessed it, T, and all it's going to do is return a my box with T, or sorry, X, and then we're going to implement the deref trait on it so that we can dereference the value out of box. So we'll do use standard ops deref, and then we're going to implement the trait. So implement declaring type T deref for my box of type T, and then ignore this type target thing for now. We're going to cover that in a separate chapter. It's not important right now. But what's more important is we're going to define this deref function that the deref trait calls for, and it's going to take a reference to self, and it's going to return self target, and what it's going to do is literally, this is it. It's just getting the value out of our box, more a reference value out of our box, and that's basically it. So we'd be able to do something like this. We're just going to clean this up, and we could say box equals my box new 1 2 3, and then let C equal the value that's held in B, and then if we really wanted to, we could print out C. Or I'm not in C, we're in Rust. I'll go ahead and do a cargo run, and this is going to first get the iteration, or our list, our 1 and 2. It's going to iterate through our cons list, and then we move this value. This wasn't on the heap, but we dereferenced it and we got the true value of it. As you can see, this C type, pardon the pun. I'm so good with the puns today, am I not? But it's a I32, not a reference to an I32, and we're going ahead and printing out this value itself. We're not printing out a reference, we're actually printing out C, because C is the owner of this new value, which is, you guessed it, 1 2 3. But that's it for this video. I'm going to keep these short as they're starting to get pretty dense with the information and whatnot. So be sure to check out the exercises repo for this video as well. And again, congrats, you've officially covered the basics of the language and we're starting to get into the nitty-gritty stuff. So in summary, we introduced ourselves with the cons list and up here, and why we need to be able to store values on the heap, because otherwise we're going to have infinite values on the stack, and how we could do that with the box type. We also looked at how box and other smart pointers like the one that we implemented ourselves can be treated like any old reference by dereferencing it. We also briefly covered how these references can be quote unquote decomposed into the values that they hold, in this case with current, through dereference coercion. So, see you in the next one.